Cool. Okay, cool. Yeah, so as previously mentioned, I'm falling in for BS Demon, who unfortunately got hassled by US Custom and Border people. Those guys are such fucking assholes. Right, so I'll be talking about iOS and Android security. Basically, the mobile app market has exploded over the last 2-3 years. And there's been lots and lots of demand for security reviews for iOS and Android apps. About a year and a half ago, I started doing this stuff for the company I work for, which is called iOactive. At the time, there was very little published about security for iOS and Android apps. So basically, I sort of had to set out and learn all these things because nothing had been published yet. The last couple of months, things have changed. If you happen to be at Black Hat a few months ago, there were quite a few mobile talks. So the ball sort of started rolling. I've done over a dozen of mobile app security reviews over the last year and a half. And basically this presentation is sort of the combined knowledge of all the things I've learned where security can go wrong for mobile apps. I originally started off looking at iOS apps, and so I know the most about iOS application security. Only later did I start looking at Android apps. And what I noticed was that there's a lot of similarities in sort of the security issues that pop up on both mobile platforms. And even if you look at like an API level in the programming model for both apps, they're quite similar to the point where the APIs have the exact same name and those kind of things. So basically this talk is sort of a comparison of here's what goes wrong, here's how it looks in iOS, here's how it looks in Android. With that said, basically, these are sort of the things I'll be covering from an application security point of view. First, I'll talk a little bit about the environment, and then you move on to sort of transport security, URL handlers, web views, and all sorts of stuff that sort of that you might run into when you look at mobile apps, and specifically security for mobile apps. So yeah, the application environment for iOS, it's all or most iOS apps are native apps. It's done on iOS, which is a port of macOS to ARM, more or less. Pretty much everything's written in Objective-C. Cool thing about Objective-C is that it's a strict superset of C, which means all valid C code is valid Objective-C, and C is basically sort of this bolted Objective-like language bolted on top of C. The good thing about Objective-C, though, is that even though it's native, it comes with a whole bunch of classes that do a whole bunch of low-level stuff for you. So the chance of running into memory corruption bugs is significantly reduced if you stick to using Objective-C classes. Android is slightly different. It's Linux-based or highly mutilated Linux. Most of the apps for Android are managed code. It's in Java. They've got the Google guys came up with their own VM. They don't use Java VM. They use a thing called Dalvik. It's more or less source compatible. It is not binary compatible. The cool thing about Android is that if you want to, you can also write native code using the NDK, which is called the Native Development Kit. As far as I understand, I think it's mostly there so that if you want to port desktop apps to Android, and you've written your Windows desktop app in C or C++, then the NDK makes it significantly easier to port stuff over. Whereas if you have to do a complete rewrite in Java, it would take a lot more time. Okay, with that said, let's dive into transport security. Obviously, there's a bunch of mobile apps that will want to do transport security. You know, mobile banking, mobile stock trading, sales apps, all those kind of things. You don't want your private data to leak out. They will most likely use SSL. I mean, if not, and if they end up rolling their own, that's a bug in its own, but hopefully they'll be smart enough to use SSL. On iOS, the way you do that is you basically use the HTTP classes, in this case NSURL connection and NSURL request, and you just give it a link which starts with HTTPS : / and it will do all the SSL for you. Problem is that there's a bunch of default ciphersuits which are on by default. Obviously DES, and then 40-bit DES, 40-bit RC4. Really weak stuff, which you can actually crack almost in real time. So this is So DES, 40-bit DES, 40-bit RC4, and then a few others. All of these are quite weak and shouldn't be used, but they're there and they're on by default. What's worse is that there's no way to turn them off. You're kind of stuck with them. It's documented the way you can't turn them off, and it's documented that you can't turn it off, sort of. Apple has a secure coding guideline, and in it, it has a note which says, the secure transport programming interface is not available on iOS. Use CF network programming instead. And CF network programming does not allow you to change cipher suits. So you're stuck with these weak ciphers, and you just can't get rid of them. So the problem basically is that the APIs just aren't granular enough. They should export some method or a list of things where you can set the cipher suits, but at the present time, they're not there. Hopefully, in the future, that'll change, but presently, you can't do that. So there's no way to fix it. You can mitigate it by not using the native embedded SL stack and just to go out and just compile in OpenSL, or if you don't want to use OpenSL, there's a bunch of embedded SL stacks which you can use. Okay. Like CISL and MatrixSL, and they have a very small footprint, and you could easily embed those in your mobile applications. So the documentation said use CF network. CF network doesn't have the capability to change cipher suits, but CF network does allow you to shoot yourself in the foot even more. By default, CF network's pretty good, but it has hooks where you can say if certs come in, you can allow expired certs, you can allow expired roots, you can allow any root, and you can say don't even validate the certificate chain. Those are all possible options, but it's not on by default. If you were to turn this stuff on, it kind of looks like this, where you just set a bunch of keys and set them all to yes, and then you sort of you set these properties in a CF read stream, and then you're good to go. Then all of a sudden, so if you were to use this kind of code, the cert, you would allow expired certs, expired roots, any root, and not validate certificate change, which is obviously quite bad. Luckily, none of that stuff's on by default. It takes a lot of work to actually screw this one up, but it's not unthinkable. I looked at one particular app, and this code was in there and was used for debugging purposes, except there was no if-def debug. So if they had shipped without us looking at it, they would have shipped with this code on. So it can happen. Transport security in Android is not that much better. The defaults are equally bad. These are the same sort of ciphers which are supported by default. DES, 40-bit DES, 40-bit RC4. Very weak stuff that you don't want to be using. It's slightly better because you can actually fix things in Android. Java comes with a bunch of APIs which allows you to change the cipher suits. And so if you use the set enable cipher suits API, it kind of looks like this. So you have to sort of make your own sockets and go a little bit more low level. But you can actually change the cipher suits that you want to use. So in this case, for example, the only cipher suits I've supported is TLS RSA AS 128-bit. This one would be a lot more secure than the previous ones. Okay, moving on to URL handlers. URL handlers in iOS are a great entry point because they're not just, they're sort of seen as a way to do inter-process communication. So by default, iPhone doesn't allow apps to share data with each other. They want to have complete segregation of apps, which from a security point of view is a good idea. But it becomes a problem because developers are kind of stuck and there's no way for them to ever share between apps, and sometimes they want to do that. So developers basically sort of worked around it by saying, we're going to use these URL handlers, and we're going to use them as IPC mechanisms so that other apps can talk to us and send us information. Initially, it was sort of a hack, and then Apple kind of sort of condoned it. And then now it's actually officially supported. If you go look on Apple's developer website, this is now a documented way to do IPC between applications. The way it basically works is an application can just register URL, and then other application can call it, and it's an IPC mechanism. And it was originally, I think, found or done by these people through Mobile Orchard. And if you go to that website, it lists sort of how to do it. In short, basically the way you do is you have an XML file or a plist file, and you say URL, and then you say my protocol, and my protocol will be your URL handler. And then you basically define a callback, which is called handle open URL. And then once you register your URL handler, the iOS itself will go to your app and it will call the handle open URL method and pass URL data to it. And so that's how data comes in and you can start handling this stuff. So handle open URL is a good entry point if you have to audit iOS applications. Problem becomes any application or any web page can now also call into your app and give it data. So it's an unforeseen consequence of this IPC mechanism is that you're not just exposing it to your local apps, you're exposing your app to the internet. That's a bad idea. It's still kind of, it would kind of suck if you have to social engineer someone to browse to your website from their mobile, from their iPhone, and then go to your website and they still have to click on something before you can exploit one of their apps. So when I stumbled upon this, I was like, well, maybe isn't there a way I could force someone's iPhone to go to my website, and then from my website, open up a bunch of apps or call URL handlers and apps and try to exploit a bug in there? And it turns out that there's a way to do it. In iOS 3 and above, there's this Wi-Fi hotspot feature. And basically what it does is if you connect to a Wi-Fi, the first thing it does is it goes out to www.apple.com. And if it comes back and says 200 here's Apple, then it says, oh, you're good to go, you're on the internet. If it doesn't, and it detects a 302 redirect, it says, oh, you must be on a Wi-Fi hotspot, and I'll redirect you to the page where you have to log in and pay by credit card or whatnot. And it pops up a browser with that redirect page. It kind of looks like this. This stuff happens automatically. As soon as your phone connects, this thing pops up. So we can obviously abuse this stuff. If we know an iPhone's on a network, we can knock them off the network. The iPhone will automatically try to reconnect to the Wi-Fi network. And then you spoof a 302 because you're in the same local network. And then this thing pops up, except now it won't be this page. It'll be my malicious page. And my malicious page is basically going to call a URL handler and try to exploit a bug in one of the applications which has a URL handler. This stuff's on by default. On iOS 4, you can turn it off. On iOS 3, I couldn't find a way to turn it off. I haven't tested iOS 5 yet. What's cool is that when Apple officially started supporting URL handlers as an IPC mechanism, they sort of said, well, we got to do better and try to help developers a little bit. Because with URL handler, you have to sort of serialize and deserialize everything yourself, and the chance that you screw something up is realistic. And so what Apple did is they came up with a new API to do it. Instead of handle open URL, it's just called open URL. And it's got a bunch more arguments. First of all, it tells you which application called you. And then it allows you to basically serialize over data instead of just giving it a string with URL stuff. But the source application stuff is actually kind of interesting because it tells you who's calling you. So now you can look at source application and say, oh, if this is mobile Safari, I'm not going to handle this stuff because it's some malicious website that's trying to send me stuff. So you can build a whitelist of apps that you would support, or you can build a blacklist of apps that you won't support. So OpenURL is definitely the better choice. It's a much more elegant API, and it allows passive objects instead of having to serialize and deserialize data between applications. On Android, things are slightly different. There's a way to do IPC. Basically, the permission model on Android is very different. Since Android is basically sort of a modified Linux, every app runs as its own UID. And then there's the mechanism in place so that apps can talk to each other. And this is called activities, and you have to program them into your app. And this is only local stuff. The browser can't touch it, but apps can still talk to each other. And because they've got different UIDs, there's a distinct privilege between both apps. Basically, the IDs, this stuff is designed so that apps can talk to each other. But it can easily lead to repurposing attacks where you expose one feature to an application, and then the application can go ahead and do something else with it. For example, there's been a number of apps that I've seen for Android that allow you to talk to some online web service and then submit documents or do Twitter updates or whatnot. And it would expose an intent to a local application, and a local application would just go talk to your intent and send over this stuff. And the application itself, which exposes the intent, does all the authentication, and all the stuff happens by default without the user knowing about it. So if you have a malicious app installed, they could just use that intent. The way you do this stuff is you have a manifest file called Android manifest.xml, and you just declare the activity in there. And then you have to set the export attribute in this Android manifest file. But this thing's documented, it's quite complex. It says, the default value depends on whether, the activity contains intent filters. In the absence of filters, the activity can be invoked and so forth. If at least one filter is defined, but you didn't say export, then it's exported anyway. And then it says, besides that, you can also use permissions, and this is just a small snippet of a long document. This thing is quite complex, and you never really know if an activity is really exposed or not. Or at least I can never figure it out. The way to do it is just run the app and enumerate and see if you can actually talk to it or not. If you just look at the manifest file, it's kind of up in the air whether or not it's exposed or not. It's kind of a shot in the dark. So yeah, the exporting of activities is kind of complex. I wish it was a lot more simpler. If this one's defined, then it's exported, but if it's not defined, then it might be exported and so forth. I couldn't figure it out. Okay, moving on from there, in iOS, you have this thing called WebViews or UIWebViews, and what that really is that you can embed a browser into your mobile application. And this is twofold. It can be used, to actually not really be a browser, but just use the browser as your GUI. And so you build up some HTML to do a GUI instead of program the GUI in Objective-C. Or B, it can actually be used as an embedded browser to render some HTML. And basically just have a normal browser embedded into an application. So let's go look at both cases. If it's used to build up a GUI, then it's really part of your application and not just some embedded browser window. Now, obviously, that means you're potentially vulnerable to attack if you're using it as a GUI, is that if any user data ends up in your GUI and it's not properly escaped, you end up with cross-site scripting inside your application. Now, cross-site scripting on iOS is slightly different than when you're just doing it on a web app. So by default, the WebViews don't support bridges from JavaScript to Objective-C. But certainly for when you use WebViews as a part of your GUI, developers sort of want to have JavaScript to Objective-C bridges. So you can write a bunch of JavaScript and say, go refresh, go update this window, or go do this, or call this method, or do so and so. And you have to have a way to go to Objective-C and say, do this. And so when people use UIWebViews as part of their GUI, they usually make Objective-C bridges. And that's kind of interesting because all of a sudden you have this thing where if you got a cross-site scripting vulnerability, then your JavaScript all of a sudden isn't just a web thing, it gets to call native methods, which is kind of dangerous. And the way people make these bridges is that you have URL handlers, and these URL handlers are different than the one I talked about earlier. These URL handlers are specific to that UIWebView. Only that window will have that URL handler. And the URL handler is called a should start loading with request, basically. And if you implement should start loading with request, you can make it do anything you want. So most UIWebViews will take deserialize a bunch of arguments and then say, call this one, or call this one, or call this one. But sometimes I've seen some that are a lot worse, where it's sort of a wildcard, where basically the way it works is you do a JavaScript call to this URL handler, and the first thing it says is, this is the function name I want to call in the native application, and these are the arguments I want to give it. And this is kind of what it looks like. And this is stuff you don't want to do if you're writing mobile apps, but this is what it looks like. And what's interesting is that, so when writing iOS apps, there's a very large community around these things, where people say sort of, here's sample code, and here's how to do X, Y, Z. And this is one of these things I found on a heavily used community website. And I'm willing to bet there's a number of iPhone apps which just copy this stuff just one to one. And so basically this stuff is, you have your should start loading with request method, and then You take your components with it, you take your function name, and it calls a perform selector, and then basically the function name is the function of your an Objective-C function, and it just calls into an arbitrary Objective-C method. If you got cross-site scripting and you do this, the app's completely owned. I mean, you can make it do whatever you want it to do. If it's used simply as a browser, things aren't quite this bad, but they're not that good either. Turns out that the WebViews or the browser on Safari is quite powerful, and it can do a lot of stuff. It can render a lot more than just HTML. It can parse a very large number of file formats, specifically Excel, Keynote, Numbers, Pages, PDF, PowerPoint, Word, RTF, Zip, and then different versions of Keynote, Numbers, and Pages. That's quite a long list of stuff, and these are a lot of file formats which are incredibly hard to parse. I mean, I've never seen anybody make an Excel parser which didn't have at least one heap overflow, right? So these parsers are not to be trusted, right? Now, and it's not just that the parsers themselves can have bugs. Like the Excel parser isn't just an Excel parser. What it does, it's more a converter. It takes an Excel file and it converts it to HTML, which means now you also have to worry about HTML injection, where if you get an Excel file which doesn't properly get converted, then you might have cross-site scripting because this thing's trying to load an Excel file. And it happens in the current DOM. So let's say you have a UIWebView which goes to your corporate website, and I can upload an Excel file there. Then all of a sudden, when the iPhone app renders this stuff, I now have a cross-site scripting bug inside your corporate website, and I can steal your cookie and basically become your web user because of using UIWebViews. They're Apple APIs, so it's not really the developer's fault, except it is in your process. So when this stuff happens, it does happen to your application. The support for all these file formats on by default, at the present time, you can't turn it off. So it's there to stay. If you load an arbitrary HTML page, anybody who can provide that HTML page can call any of these file parsers. UIWebView do a number of other things. Also has support for like telephone URLs. At least iPhone does. I don't think iPad does. Good thing about telephone URLs is that you can actually turn them off. It's a property which you can just set a Boolean property which you just set to no, and then it won't parse it. The only mitigation I really have for using of UIWebViews is render out of proc. So don't have a UIWebView and just go out and get mobile Safari to render stuff for you. That way, if someone's trying to attack your app by feeding loose HTML or trying to break your browser somehow, is that they would get to exploit Safari and not your application. It's attack surface reduction. It's not great. It's the best I can come up with. In Android, they've got almost the same thing. They don't call it UIWebView, it's just called WebView. It's very similar. It can also be vulnerable to cross-site scripting if your developer doesn't carefully use WebViews. And so WebViews are slightly different in that they actually do have a supported way to write JavaScript to Java bridges. It's basically called add JavaScript interface, and you can basically get it to go and get your JavaScript to go and use Java classes that you've defined. So moving on to the next part, this is iOS specific. This is basically the use of what's called UIImage, which is sort of a container class, which can handle a whole bunch of image file formats. And it's quite similar to the UIWebViews. The attack surface in that it's not just one little thing, it supports a very large number of file formats. In this particular case, TIFF, JPEG, PNG, bitmaps, icons, cursors, XBM, GIF. And then on top of that, there's also embedded formats inside of some of the formats, such as EXIF and ICC profiles. Again, all of these things are very complex binary file formats, which everyone has screwed up at least once. So it's an enormous attack surface right there. And there's no property to say, I'm going to use the UI image, but when I feed an image that I fetch over the internet into it, I want it to only support only ping or only bitmaps. There are, however, two workarounds. UI image basically allows you to either point it to a URL, and it'll go fetch the image and just render it, whatever type it is. Or you can give it a core graphics image reference. And if you give it a core graphics image reference, you'll just use that one. And the cool thing about if you use core graphics is that in core graphics, you can have specific APIs say, this is a PNG file, this is a JPEG file, this is a bitmap file, and so forth. So you can just use core graphics to load an image, and then you pass off the core graphics image reference to UI image, and then you can start using the image. And that way, the attack surface is much reduced. Or the other thing you could do is before you actually pass the image to a UI image, you download it and you look at the header file. And each particular image format has its own set of magic. So for PNG, it's 137, 80, 78, and so forth. And there's another one for GIF, another one for JPEG, another one for bitmaps, and so forth. So you can just scan the magic values first, and if those don't match up, just ignore it. Otherwise, you can pass it on to UI image. And moving on to HTTP header injection. This is clearly not mobile specific, but it is incredibly common in web apps. Most web apps I've seen that do online stuff tend to talk to web services. And since web services go over HTTP, it's very common to see HTTP header injection bugs in the web app, in the mobile clients. Basically, if the developer starts rolling its own HTTP client code, they're probably vulnerable. HTTP header injection is basically because they'll forget to escape stuff like in the next line and that kind of stuff. And then you end up with an attacker might be able to inject its own HTTP headers, in which case you might be able to get an attacker to sort of say stuff on your behalf to a web service that you really didn't intend to do. Or just sort of arbitrarily inject HTTP requests as you. This is a very simple example of some stuff I've seen, where basically as part of a HTTP header, a name of a file name gets attached and a content type. And so let's say if you're a control of part of the file name, you could just have a next line of file name, and you now all of a sudden get to inject HTTP headers. Some good stuff on the iOS side is iOS actually has fairly decent APIs to do HTTP header stuff. You basically use the mutable URL request objects, and on those you call the add value or set value methods for HTTP header field. These are not vulnerable to injection. They will actually not take next lines. What they do is they just fail silently. So if you put in a header and they see there's a next line in there, it doesn't actually succeed, doesn't put the header in the request. It's not great that it's failed silently because it's not documented, but I'll take this over being vulnerable. So I'm okay with this, but it's sort of depending on how you stand on this issue. Android's slightly different. Android has a few APIs to build up requests. The one I've seen used the most is Apache HTTP components, and this is basically the org.apache.http package. It's basically HTTP request.add header. This is a very, very low level API, and it does not encode anything. It basically takes a binary stream of stuff and just puts it in the request. Doesn't validate anything, which means if an attacker gets to put header value into some HTTP request, you as the developer have to do your own validation and make sure there's no next line there. If you don't do that, you're kind of host and you're vulnerable to HTTP header injection. This is kind of what it looks like in a sample Android app. And so basically this is my proof of concept where you do a request add header, and I do header 1, and then the content of it I do AABB, and then next line I say injected headers and so forth. And then I have a fake web service, which is basically just netcat. And if you look at the I don't know if you can see it, but if you look at the netcat data, it basically says, the get request, and then a host field, a host header, a connection header, a user agent header, says header 1, and then on the next line it says injected header. So this is basically a proof of concept of how you would inject headers into a vulnerable Android application. Okay. Again, this one's iOS specific. So as I said earlier, that iOS apps are mostly native code, but they use Objective-C, and if you stick to Objective-C syntax and Objective-C classes, as a developer, you're mostly safe from memory corruption bugs and that kind of stuff. So there's one exception, basically. which is a lot of these, or a number of Objective-C classes have their own format functions, and they are just as vulnerable to format string bugs as any other C application if you don't know what you're doing. So obviously, if you've got format functions, then they can be vulnerable to format string bugs. From what I've seen, almost every iOS app I've ever looked at, I think out of a dozen or so I've seen, 10 or 11 of them have had at least one format string bug. So it's rampant among iOS apps. One of the most common bugs, basically, on iOS apps. I think it's because most iOS developers aren't C or C++ programmers, and so they've never been exposed to format functions, and they don't really know how bad it can be. That's my only guess. But basically, the vulnerable Objective-C methods are the one I'm listing. NSLog is one of the most common ones. String and format, int format, pen format, exception format. So any of these potentially vulnerable to format string bugs. Obviously, since Objective-C is a superset of C, the C format functions also come into play. So if you have an iPhone app which has some C code in it, and you use printf or snprintf or fprintf, gotta watch out for format string bugs in those, obviously. A word or two about exploiting format string bugs or Objective-C format string bugs is that they're slightly different from the ones in C and C++, because there's no %n. %n is missing. I don't know if that's done on purpose or by accident, but it's not there. And so I sat there kind of wondering, well, if %n isn't there, it becomes hard to exploit these things, right? And so I started looking at the documentation for these Objective-C format functions, and I see there's a %@ format specifier. And it turns out what that one does is documentation says, for a %n specifier, it says the string returned by a descript with local method, if available, or the description method otherwise, which basically means that %at will pop a pointer from the stack, which is an NS object, and it will call methods on that object, which, it's a win right there. You're pretty much done. I mean, you get code execution out of that one. There's a couple of jumps, more hoops to jump through. Basically, I wrote a sample app and sort of worked my way through it in the debugger to try and get code execution. This stuff's kind of boring, and I need to run through it because there's other stuff I got to look at. But if you're interested, I can send you these slides, and step by step sort of says what you have to do. Eventually, basically, if you want to know exactly what to do or how to build up the stuff, if the NS object you want to put on the stack, the pointer, so it has to look like this. So if you write this kind of C code, basically in the first you say no byte, second one is a dummy, third one. So you just fill out those exact pointers and you put them on the stack, and you get format string functions of %at and point to that one. You'll get code execution by filling out this EIP that'll point to anywhere you want it to point. The next thing, again, this is iOS specific. So as I said before, Objective-C is a C superset, and you're mostly safe if you stick to the objects. The one thing where the objects kind of suck and don't really help you that much is when you're parsing binary protocols. There's no good Objective-C methods and classes for that stuff. So if you're writing an iPhone app and you have to deal with binary protocols, you have to sort of fall back to good old C code and try to do binary protocol handling correctly in C code. We know that's hard. We know almost everyone that's tried to do binary protocol handling in C has at least at one point in time failed, and it had a massive security bug. Even OpenSH has had a few. So when you see binary protocol handling and you see C or C++, you know there's going to be bugs there. You know there's going to be heap corruptions or stack smashes there. So basically, when developers fall back to this one, certainly for iOS apps, you can already smell the bugs before you've seen a line of code. Another one which is quite common on both iOS and Android is are directed reversals. iOS has similar file APIs to Mac OS X, and so those can be vulnerable to directed reversals. This is when you use the NS File Manager class. And this is, for example, a very trivial example of a directed reversal where basically you create some temporary directory and then you append some attacker-controlled string to it, and then the attacker could basically be like .. // / / / and then whatever file you want, and then it'll read or write to that file. This is a very classic directory traversal. These are quite common in iOS apps. But it gets a little bit more interesting sometimes because sometimes you'll see people be like, oh, why don't we? I'll be smart, and what I do is I'll add an extension to it, and so that if you try to open, even if you do directory traversal and you try to open a file because you have .dot extension, the file won't exist, and the open or the read or write will fail. That doesn't quite work the way you want it to in Objective-C because Objective-C NS strings are different from C strings. In a C strings, obviously, the null byte terminates the string, whereas in NS strings, the null byte doesn't terminate the string. So you can have this kind of code, which takes your attack control data and then appends a string to it, and your attack control data can have a null byte in it, which will be seen as one big long string in Objective-C. But then the moment where you pass it on to operating system call, which are written in C, they'll see your first null byte and be like, oh, wow, that's the end of the string, and truncates the extension. The extension's gone, and all of a sudden you come back to a simple directory traversal. So poised null bytes are there and are quite common on iOS apps. Things are pretty much the same on Android. Android, you can use Java's file APIs, and so it'll kind of look like this. And so it's quite, if you don't watch out, you just take user control data as a file name, as part of the file name, your Android app might be vulnerable to directory traversals. Again, poison null bytes there too, because Java strings are not C strings. Java strings will happily take null bytes, and then once you go to the syscall level, it'll see the null byte and doesn't take, basically truncates the extension. So this basically maps one-to-one for Android and iOS. It's very similar. XML parsing is because most iPhone apps or iOS apps, when they go talk to online services, they usually web services, and if you use web services, it means you're talking XML, and so you have to have an XML parser in there somewhere. NSXMLParser is usually used to parse XML files, unless you roll your own. But I've mostly seen people use NSXML. It's got these on by default, which means you're potentially vulnerable to billion laughs attacks. You can't really turn it off. That doesn't resolve certain uncertainties, which is at least something. You can't really turn it off. So this is kind of, if you want to do a billion laughs attack, this is what it looks like. And basically, it's sort of a self-expanding thing. And so if you run this thing into an XML parser which supports CDTs, it just sort of hangs there and kind of freezes and doesn't do anything until eventually it runs out of memory and the thing crashes. So you can't turn it off, but there's kind of a workaround. The way NSXML works is basically you can define a bunch of callbacks, which is if you see this, call this callback. If you see this, call this callback. And so what you can do is you can have callbacks for DDTs, and you can say, found element declared with name, or found attribute declared, or found external entity, or found so-and-so, call this callback. And so if you're writing iOS apps, you can basically declare all 6 callbacks, and if any of those callbacks ever get called, it comes through DDT. And if you don't want to do DDTs, you can just say, oh, this is a potentially malicious input. I'm simply not handling it. So it's kind of hairy, but it works. Obviously, the other thing is that with XML, you got to be very careful. Once you start parsing stuff recursively, you quite easily come in this position where you sort of blow up the stack because if you got a very long and very deeply embedded XML data, and you keep calling your own function, then eventually you blow up the stack. Very common, obviously not mobile specific, but it's quite common on iOS apps. So the way to fix that is you want to have some recursion in place. So that, say if we've recursed 100 times, then if you recurse 100 times, it's probably malicious XML data and not going to handle it. The last XML kind of thing is where you can have XML injection. Again, mostly happens when you're talking to web services. Not mobile specific, but very common in mobile apps. Both Android and iOS. And basically, if you just take potentially that control data and you stick it into XML requests that you send off to a web service, and you don't encode them properly, then obviously you can have XML injection, depending on what the web service allows you to do, may or may not be critical. So obviously the thing to do is to do proper XML escaping of any potential attack control data, and you're safe. On Android, it kind of looks like this, for example, where basically you just build an XML string and you take some data that a user gave you and you put it in the XML, and since it's not properly encoded, this one line of code is vulnerable to XML injection. Another thing is, again, SQL injection, obviously not mobile specific, but it does come into play in mobile. Most of these mobile platforms, both iOS and Android, come with SQLite, and if you're not careful, you can have SQL injection in your SQLite database, and it might allow an attacker to input stuff into your database or potentially, suck stuff out of your database you don't want them to see. I'd imagine you all know what SQL injection looks like, but if you don't, this is kind of what it looks like. If this is stack controlled, then you basically do a select, and then so you can sort of inject SQL into this one. Obviously, Android is quite similar when it comes with SQLite, and you use they've got Java wrappers around SQLite, which is android.database.sqlite. APIs are very similar to the SQLite C APIs. Kind of looks like this, and so if you're not careful, you can have SQL injection in that one too. Okay, the last thing I'll be talking about is something I stumbled upon. This is very Objective-C specific, and I've seen this actually quite a lot in quite a few iPhone apps. So basically, all classes that you define in Objective-C all inherit from the same base class, which is called NSObject. And there's a catch-all class for NSObject, which is called ID. And so you can have type confusion attacks, where if you have a method that returns ID, and then you assign it to any number of class, then the assumption is that you know what's going to be returned is the class that you want it to be. But if that method happens to return a different kind of class, then all of a sudden you think it's class A, while what you're really pointing at is class B, and so you can have type confusion attacks. They're actually quite common in a bunch of mobile apps. And so the reason why this works, or why this kind of confusing, is sort of because Objective-C is slightly different from other languages, where because you can have your pointer can point to a different class, and then you can still call methods on it. But these methods, they're not like in C or C++, where it's a function pointer. What it really is method names get resolved in runtime. And so if the method exists, then they'll actually call the method, even though if you call a method on class A, but you're really in class B, but it has the same method name, you're calling it a method with the same name, which can do something completely different. Obviously, this method doesn't exist on class B. It'll just throw an exception. So yeah, this is sort of the idea where let's say you have a class which you call blah blah, and then has a method called object for key, and then something returns an ID, and you think it's a dictionary, you call object for key on it, but it's really your blah blah class, and now you're calling the object for key method on your blah blah class. Depending on and if the class doesn't exist, an exception gets thrown. So either way, either the app can crash, or you can have severe consequences depending on what the function that's implemented really does. This is very common, for example, when parsing JSON on iPhone apps. The most common JSON library for iPhone is called SBJSON. And what SBJSON really does is it extends or overloads the NS string class, and you can call JSON value on it, and basically you get the JSON value back, a serialized JSON of a JSON string. And clearly it just returns ID. And JSON can basically return NS dictionary, NS array, NS string, Boolean, integer, and null, so 6 different types. And so if you basically take the type back for JSON value, and you don't actually check the type that's returned, and you just say, oh, I know this is NS string because the service always gives me an NS string, and you call NS string APIs on some other class, which is an NS string, then either you're going to get an exception, or you're going to be calling methods which you shouldn't be calling. So basically, before when you get something with an ID back, before you actually use that class, you want to make sure that it's of the right type. And the way that works is since everything's inherits from NSObject has a method called isKindOf class. If you call isKindOf class, you can test what kind of class it really is. Okay, that's it. I hope you all enjoyed it. If anybody's got any questions, now's the time to ask. Yeah. How many apps I've seen so far? Slightly over a dozen. I think 13 or 14. Cool. Any other questions? I don't know. Yeah, I don't think you're supposed to do that. I think as an app you can't do that. I'd have to go back and check, but I don't think you can do that as an app. Yes? Given an app that uses the default slash weak ones on the client side, are there actually practical tools to use man-in-the-middle that? That's a good one. So this is about the weak weak cipher suits, right? So hold on. So what's interesting is that so there's actually a whole bunch of server sides SL stacks that support it. It's about half of the ones I've tested support weak ciphers on the server side, and the idea there is that it's only there for app-compat for really old applications that want to do it. And the assumption is that new clients would never, ever support these very weak ciphers. Now, if you got both the client side and the server side having these weak ciphers, you can try and steer the service or the server to try and select the weaker cipher. In laboratory conditions, I've been able to get this done. You can't actually spoof the packets because you got integrity checks. But the way the server side works is it basically goes over the list of ciphers it supports, and it goes over them by strongest to weakest. And so it'll try to select the strongest one first. But there are some cases where, for example, it says, goes to the strongest one and says, oh, I support this one, and the client side has it too. Oh, that's great, I'll pick that one. And then tries to do a whole bunch of initialization. But then, for example, they'll do some malloc, and if a malloc fails, it goes like, oh, malloc failed, then it can't support this one, and it goes back to the beginning of the loop, it takes a second one. So you can get, so if you as a malicious attacker can steer a service into having a limited amount of memory while going through that loop until it goes to one of the very weak ones, and then all of a sudden memory clears up and says, oh, I know this 40-bit DES cipher and I support it. Why didn't I go initialize these structures? And all of a sudden memory is available, it locates the stuff, and now you're talking about over a 40-bit DES, which you and I, we can both crack. So yes, it's possible to do it. It's very hard, and I'd say in laboratory conditions, you can do it. In reality, it's quite hard to pull off reliably. Is that, yeah? Can you say it again? You can't do that because there's integrity checks, right? So if I'm in the middle, if I do an X man in the middle and I fake the client, then the server goes back to the client, and the client says, this is not what I told you. Now you can do other things though. You can man in the middle and you can delay these things. So you can delay them. So you send out these things. So you do your denial of service first to try and minimize the memory. So you can optimize your attacks. So you can delay packets, but you can't change the content. All right. Any other questions? Yeah. Okay. Uh-huh. Not that I know of, but it wouldn't surprise me if that happens. That's the best answer I got. Yeah, cool. Any other questions?
Is that it?
Yeah, cool. Thanks for listening.
All right. Round of applause for Ilja.